2012, the university population of a country was 160,000 and increasing at an annual rate of 4.5%. The growth in the university population can be represented by a function. Okay, so it's at 160,000 now, and it's being multiplied by 1.045 every year. Notice, we're not just multiplying by 0.045. That would mean that every year we only have 4.5% of our students left, and the other 95.5% are dying or disappearing or something. Multiplying by 1 means, okay, we've still got all the students we had before, plus we have another 4.5%. So this is how you do an exponential growth. You should have a number bigger than 1. And you multiply by how many years have passed. That's your n value. So if this is an equation of the form ab to the x power, what are the values for a and b? Well, a is the multiplier out front, so that's 160,000. It's also known as your initial value or your start value. And b, the number we keep multiplying by, is 1.045. Use a graphing calculator to graph the function which will show the population growth from 2012 to 2040. Well, this 160,000 is the value for 2012. This, in 2040, is 28 years later. So when you graphed this, you'd have y1 equals 160,000 times 1.045 to the power of x, assuming your calculator doesn't have n in it. And for your windows, you'd want to have an x-min of probably 0. That would start you right at 2012. And your x-max would be 28, meaning 28 years later. That'll take you to 2040. For y's, it is always nice to have your minimum at 0. And for your y max, well, it's growing like 5% a year. 5% of 160,000 is 8,000. If that happens 28 times, we're talking another like 250,000 students, plus it's compound, so even 400,000 may not be enough. I will hazard a guess that 500,000 would be enough to cover all this. And now that I have opened my mouth about that, let's see if I'm right, or if I have to live in shame for the next several days for giving you a bad estimate. Okay. The most that number could ever get to at the very end of the graph is 160,000 times 1.45 to the 28th power, and that comes out to, even 500,000 isn't enough. I underestimated the power of compound growth. I'm sorry. Y max should be more like 600,000 if you want to see this entire curve at once. And because I see the other questions are talking about graphing calculators still, I guess I should put this thing in here. 1.045 to the power of x. And I went from 0 to 28 years in the future. Start the y minimum at 0, and for the max we'll go up to 600,000. And that's what exponential growth looks like. Beautiful. Okay, what else do they want? Use features of the graphing calculator to determine the population in the year 2015. This, 2012, is our very first year, so 2015 is only 3 years after that. If you want to find that on the calculator, you go to Value and give it 3 years. That says 3 years in the future, how many university students will we have? And there's your answer, 182,500. So to get that again, you go second trace, pick value, and then it says, okay, what value do you want? We say 3, please. Enter, and finds the value exactly at that year. And finally, the number of years required for the population to double from its 2012 size. So we're at 160,000. Doubling would mean we hit 320,000. I'll just put in that line. There we go. Here's our original amount. Here's double that amount, and we hit it right there. quick and dirty answer, hit trace, move the bug until it's right over that intersection point, and you get, it'll take like 15.78 years for them to meet at 320,000. So we'd round that to about 16 years in the future, which is about the year 2028. If you want to do it exactly, second trace, intersect, and just mash enter until it finds an intersection point, and again, it agrees about 16 years until we get to 320,000.